SwayamPrabha. Digital India. Educated India.
Hello, welcome to Astrochemistry, and this is lecture 16. Now, in the previous lecture, that is lecture 15, I introduced you to the diatomics. I introduced you to the various diatomic molecules, not all of them, but some key molecules that have been detected in space. I gave two separate categories of them. For example, the one comprising of the list given in A and the other one given in B. The distinction, I said was that some of these, we stopped with looking at these molecules, and I said that these molecules, SiO, TiO, ALO, etc., they form the monomeric units, that is, the single entity responsible for the formation of the rocky ambience present in the meteorites, okay, and asteroids. So this is the second category of molecules, wherein you have some sort of a transition metal or a metal or a metalloid species from the second period or so or more bonded to oxygens. Okay, whereas in the first category we have the molecules which are primarily from the first period. Okay, I'm talking about the period starting with lithium. Okay, right, and in the periodic table, and there are some molecules containing phosphorus, sulfur, and chlorine also. However, these don't typically polymerize as much as these molecules do. Okay, when I say polymerize, I'm talking about the formation of a lattice and the generation of rocky substances. So that's why they are put in two different categories. And say, for example, some of these molecules, such as carbon monoxide, right? They can also, say, for example, carbon monoxide, they can form ICIS in the ISM itself. That is, like multiple carbon monoxide entities can be coming together. They can be predominantly weakly bound. Okay, there would be some covalent bonding also, and they would be forming ICIS in both the ISM as well as in the comets. Okay, so that is the some sort of not too strict distinction between the different types of classes of diatomics. Now, if we focus our attention, to the second class of molecules, that is SiO, TiO, and ALO. For example, if you consider the molecule SiO, just take for example SiO. In the tutorials, I gave the bond energy of a single SiO bond. Can someone recall that value? What is it? It's of the order of roughly the bond energy of SiO is approximately of the order of 450 kilojoules per mole. Now, what are the implications? The SiO bond is actually very strong. The SiO bond is exceptionally strong. And what is the normal valence of silicon? So your SiO can, further react. For example, in the molecular clouds in the ISM, SiO can further react with a similar species. I'm not going to depict the exact equation. So you can form SiO4 4 minus. It's a monomeric entity. Okay, right? This is SiO, and because the valence of silicon is 4 normally, okay, right? Now, even in the ISM, under certain conditions, this can form SiO4 4 minus. All right. Now, what does this SiO4 4 minus look like? Well, based on your intuition from general chemistry classes, it's a bit like methane, right? You have like, instead of CH4, you have SiO, and Si is right below carbon in group 4, right? So what would you, if you were asked to predict the structure for SiO4 4 minus, what would you do? based on the knowledge gained so far in chemistry, you would probably, okay, well, right? It's going to be a tetrahedron, correct? I mean, it's a two-dimensional board, but you can assume that the silicon is in the middle of a three-dimensional tetrahedron with the four edges being occupied by the four oxygens, and of course, the negative charges being there. So this is the monomeric unit of SiO4 4-. Now, SiO4 4- itself has not been detected in the ISM. Only SiO has been detected. But this molecule SiO can react further to give this SiO4 4-. And what is so special about this molecule? Why have we chosen this, in this class? Why not any other molecule? Why focus on this particular aspect? It is because this SiO4 4- can further, right, through all of this O, they can form a multiple bonds with again Si, right? All of these oxygens can form bonds with Si here, and the same unit can repeat multiple times. And what it does is, this polymerizes further, where N is a large number. Okay, are we clear? So you have this polysilicate, and once this polysilicate is formed, what happens? This monomeric unit, see, assume that this is in the gas phase, okay, right? This is in the gas phase, and perhaps this may also be in the gas phase, if you talk about a single monomeric unit. But as it polymerizes further and further, you are taking more and more atoms together, right? The packing is going to be more efficient. Molecules are coming closer. As a result, what would you expect this to be? The polymer? What would you expect the structure to be? What state of matter would you expect it to be? Solid, liquid, or gas? Liquid would be a good guess, but as it turns out, right, the molecules get packed even further than a liquid, so it's actually going to be a solid. Okay. And what type of a solid? Because the bond energy is 450 kilojoules per mole in one SiO bond, and look at the number of SiO bonds that are getting formed. And why is it getting formed? Because of the propensity for silicon to propagate along all three dimensions due to the exceptionally higher SiO bond energy. Okay, so subsequently you have this huge polymeric solid structure formed, and that is what manifests in the rocky substances of asteroids. All right, so the simple SiO detected in the ISM, as more and more molecules of SiO accrue together, right, you can form an SiO4 4-. I haven't given the exact chemistry. We might discuss it in the tutorials, but for the purpose of this lecture, we'll just move on. Okay, so once this forms, this can polymerize further. And what is the driving force behind this whole process? It is the enhancement, the enhancement in the bond energy that is going to be obtained as you polymerize it. All right, so this is a thermodynamically very helpful process, right, which results in the formation of solids. And once enough solid mass builds up, from the molecular cloud itself, from the molecular cloud of the circumstellar core, you can easily see the birth of an asteroid. So how does an asteroid form from a molecular cloud? Look at the chemistry involved there. What would we say? We would just say that, hey, as rocky mass accumulates, the asteroid is getting formed from the molecular cloud. But as part of this process, this is one example of a chemistry involved. It need not just be silicates. It can also be, like aluminum silicates. It can also be titanium silicates, etc. For example, you can form a polymeric unit from this molecule, this diatomic molecule, as well as TiO, etc., etc. But the net idea is that it's the accretion of enough of this mass, okay, right, that leads to the formation of a meteorite or an asteroid. All right. So what did we see? We started off with diatomics, and only these have been detected in space. But the rich chemistry that it provides scope for, and how chemistry explains why asteroids and comets are formed. Asteroids and comets are formed, correct? I have given you a very qualitative description, but still, despite that, you get a picture, you get a big picture of why this happens. Once we study thermodynamics, for ISM, we can actually predict how much energy would be associated with each process and how much energy would be gained in the formation of an asteroid and comets, etc. I mean, asteroids from this molecule, from this SiO molecule, right? And the comets, based on the CO ISIS. These are bond together by weaker interactions, okay, but nonetheless, they come together to form comets, right? Yeah. So by detecting the various molecules, we can predict their fate in space, and how from the molecular clouds in the ISM, much larger bodies are also generated. So that is why we chose the example of these specific molecules to illustrate this point. We shall now move on to the triatomic molecules which have been detected in space. Some key triatomics. Now, what are some examples going to be? Some examples are going to be, for example, MgNC, MgCN, and ALNC, for example. ALNC. Well, I've specifically chosen only the cyanides. Okay, I'll tell you why. And HCN, HNC, etc. So these are some molecules, right? And again, are these molecules familiar to you from this class? Well, we highlighted the example of magnesium, right? When we were discussing the differences between interstellar medium and Earth. And we saw that magnesium is not present in its conventional oxidation state that it is found on Earth, right? So these molecules will be repeatedly coming in this course, so please pay attention. Okay. So these are the triatomics. And what is the interesting scope for chemistry? Any guesses? So the scope for chemistry comes from the idea that what do metals do? What do metals do? Or metal ions more specifically? They shall coordinate or bind with electronegative atoms, right? For example, in this case, it is nitrogen. In this case, even though carbon itself is not electronegative, carbon has a negative charge here, and likewise here. And here, of course, the nitrogen is an electronegative atom. So the metal ions, right? These metal ions, these representative metal ions, Mg plus 1, Al plus 1, and Al plus 1. Okay, right? All of these metal ions, they present the scope for what is called as catalysis. Catalysis, I hope the spelling is correct. Okay, catalysis in space, which is in fact an active ongoing area of research. Okay, how do you know? Via, I'll write it better, sorry. Via coordinating with electronegative atoms. Right? This was just, for example, this molecule can react with the water molecule in space, and the Mg can also coordinate with another O also. Okay, right? And that way, it can lead to catalyzing several reactions. So that is what the metal ions do. Now, if you notice, on top of the metal ions, I have also given you, two more molecules, HCN and HNC. Now, HCN and HNC, correct? They present tremendous, opportunities for us to understand the nature of the ISM itself. I'll highlight how. Now, if you actually consider, the HCN-HNC equilibrium, okay. If you actually consider the HCN and HNC equilibrium, right? Now, it's predominantly going to be lying over here at very low temperature. Let's say, at T approximately 10 to 15 Kelvin. Why is that? Because this molecule is much more stable than this. Why is it? Any guesses? Well, because, even though nitrogen is the more electronegative atom, it is HCN which is actually more stable. Well, that is because in this molecule, okay, carbon would still be having a residual charge if you write out the Lewis structure. I'll leave it to you as a homework, or we can figure it out in the tutorials if the homework is not done. Okay, so carbon will have a net negative charge here, whereas the Lewis structure of this is fully satisfied from the requirement of any charges. So you would expect that at temperatures of 10 to 15 Kelvin, the equilibrium is towards HCN. So this should be expected to be the predominant species. Predominant. All right. That is what we would expect. Okay. However, what are your guesses? However, what's going to happen? Is the equilibrium actually going to be reversed, or will the magnitudes of HCN and HNC be more or less the same? In ISM, in the molecular clouds, okay, in the molecular clouds, the abundances of HCN and HCO, HCN and HNC, was found to be close to be 1. Okay, now isn't that a surprise? Well, you would expect that the most stable molecule is going to be formed much in greater abundance than HNC. That is a very natural expectation, right? But it turns out that the HCN to HNC ratio is approximately only 1. What could be the reason? Well, it tells you that in ISM, the chemistry is not always guided by thermodynamics only. If thermodynamics were to be a deciding factor, if thermodynamics were to be the dominant and sole deciding factor, then we would definitely expect HCN to be obtained or noticed in much higher preponderance. It should be there. The amount of HCN should vastly be greater than that of HNC. However, that is not what we note. What we note is that the ratios are more or less is equal to 1. And why is that? That is because the ISM is not guided by thermodynamics alone. It is also guided by kinetics, which plays a much more important role. Recall that highlighted this point as a difference between ISM and Earth. Whereas on Earth, eventually, given sufficient time, thermodynamics rules. Okay, but in the ISM, unlike on Earth, right, it is not always guided by thermodynamics only. The kinetics also plays an important role, and how exactly it does, we shall discuss much later. But for now, please understand that the triatomics in space, the metals bearing ones, they help us, to understand various aspects of catalysis in space, how the metal ions can coordinate with electronegative atoms and aid in chemical or molecular evolution in space. Whereas a simple molecule such as HCN and its counterpart HNC, they teach us that thermodynamic principles are not the sole guiding factors in the ISM. There could be, what else could be the other factor? It's kinetic, right? So kinetic plays a much more important role, but I am intentionally not explicitly mentioning it at this stage, because once we look into the quantitative aspects of kinetics and thermodynamics in the ISM, we shall have a much better understanding of these ideas. Okay, for now, please understand that thermodynamics is not the sole criterion. It is important, but it is not the only criterion. Okay, so on that note, let us now move on to some tetraatomics detected in space and what they teach us. What are some examples of tetraatomics? Well, for example, you can think of, this is D, you can have HCHO, for example. What is this? Formaldehyde. And didn't we start this course with formaldehyde itself in the first 1 or 2 lectures? What is the implication of formaldehyde? It contains C, H and O. And from formaldehyde, what can we get? Eventually, all the sugars, right? This is CH2O, CH2O. And CH2O n times becomes the sugars. And so your formaldehyde offers you the scope to get polymerized and form various sugars. Okay. So therefore, formaldehyde can give rise to higher molecular complexity, although the sugars themselves have not been detected in the ISM. Please note this point. But the idea that it is a molecule detected in the ISM that eventually leads to a variety of chemistry, in the planets, on Earth, etc. Okay. All right. So this is HCHO was one example. Other related examples could be something like, now this is an imine. So just like, we had the carbon and oxygen of formaldehyde, the structure of formaldehyde is going to be this, which is of course known to many of you. Okay. So this is formaldehyde and this is imine. This is like CH2NH, I believe. This is going to be CH2NH, yeah. Oh, sorry, this is not a tetraatomic. Okay. This is actually from, so HCHO is there. And the another example could be, if I'm correct, it should be HCCN, yeah. Now recall, so we had understood about the formation of the cyanoradical. The cyanoradical, we discussed it as a diatomic noticed in space. Now when this radical, associates with the CH moiety, okay, you get this molecule. Now something is, terribly upsetting, right? You can perhaps see it from my face. Something is terribly upsetting the minute I write this structure. Can you guess what is it? It is that, okay, the nitrogen's valence is what? Conventionally 3, satisfied. Carbon 4, satisfied. Hydrogen 1. But oops, I skipped one carbon, right? Yeah. What about this carbon? What is its valence? Conventional valence is 4. But here it's only bonded to 2 atoms. One on this side and another this side, right? So it's effectively going to be acting as a carbene, okay, right? A divalent carbon. So this is another example of a tetraatomic molecule, and what is the tremendous scope of chemistry it presents? Of course, to the C and N, but the most reactive moiety is going to be the divalent carbon, which will, in its quest to attain tetravalency, react in various ways. Okay, so notice that by the time we come to tetraatomics, right, we're already encountering unexpected structures. For example, a structure with divalent carbon, that goes against most of your training in high school and whatever college chemistry courses you've taken, correct? But it tells us that the interstellar medium is actually replete. It has so many of complex organic molecules. Now, let's see, the complexity need not be just only due to many atoms coming together to form a large molecule. The complexity can also be due to the fact that structurally, it goes against what you know about the chemistry on Earth. Okay, so that's why these are called as COMs in short. Molecules containing 4 or more carbon atoms and containing a carbon in them, right, are in general called as interstellar complex organic molecules. They might contain like 4 or 5 atoms and more. Okay, and the complexity again is not due to the presence of a large number of molecules, but the complexity is rather in the structure. Okay, but of course, sometimes the structure can be simple, but still they're called as complex organic molecules. Are we clear on this idea? Okay, the key fact is that the organic molecules detected in space need not always have a tetravalent carbon atom. There can be many cases where carbon atom is in its valence of 3 or 2. On Earth, we would call them reactive intermediates. We would call them as, for example, a free radical, the CH3 dot, or carbocation, which is a CH3 plus, or a carbanion, a CH3 minus. These are reactive intermediates on Earth. But recall again, because the reaction conditions, the combination of pressure and temperature, they are so different in the ISM, right? So what we would call as reactive intermediates on Earth can also exist in the ISM, and the carbon need not always be in its tetravalent state. Okay? On that note, we shall study more about the next tetraatomic molecule. the next tetraatomic molecule is going to be, this is just one, this was one, this was two. The next one is ammonia. Now, well, ammonia is a very simple molecule, right? It's a simple, beautiful, elegant molecule. Everyone encounters it, right, in their 10th or 11th standard. In the standard VSCPR model, you want to study its structure and so on and so forth, right? Now, ammonia, it turns out, is a very important molecule in ISM. Not just because it has a nitrogen and that can act as a new base or a nucleophile in reacting further, but also because this molecule, this ammonia, right, NH3, approximately in the 1960s, it informed us that density of molecules in the ISM, that is the number density, okay, right, can be as high as 10 to the power 6 even. Okay. So the simple molecule ammonia, using a very, very fundamental principle, a fundamental ground state chemistry principle, it taught us that chemistry associated with what is called as ammonia inversion. I will present more details when I tell you, how these molecules are detected. Okay, right? The idea that ammonia undergoes a certain chemistry was in fact absolutely critical to our understanding, that, hey, the ISM is not just almost empty space. It is almost empty space with some significant pockets of molecules which can evolve further. Okay, so ammonia, of course, it's also an important reactive species, but on top of that, it has taught us based on research work done in the 1960s approximately, early 70s perhaps, okay, that dense molecular clouds can also exist in the ISM. Further details, please await for 1 or 2 lectures, and I shall present the further details with ammonia and how it led to the detection of dense molecular clouds. Okay. So this is ammonia, and they're all going to be about tetraatomics. The next tetraatomic we'll be seeing is, the next tetraatomic is going to be something like H3O plus. Now, well, what is the relevance of this molecule? It's obvious, right? It is the hydrated proton, the monomeric unit of a hydrated proton, which is nothing but, you can think about it this way, right? So a proton which is hydrated by a water molecule. Okay. And what is its obvious significance? Well, it can be a proton donor, or it cannot be a proton acceptor. It can be a ready proton donor and can participate in lots of acid-base reactions in the ISM. Okay, so this is the significance of H3O plus. All right, are we clear? So imagine this, whenever you study chemistry in high school and introductory college courses, what do they always tell you? The exact structure of proton is unknown on Earth, right? Because once a proton reacts with water, it is not just one molecule of water. It is so many molecules of water coming together, and they form a complex oligomeric or a polymeric structure. The exact structure, it keeps changing because the proton hops across the H3O plus end surface. Okay, so we don't know the exact structure, so we can't find it so easily. However, in the ISM, H3O plus, the exact structure of H3O plus, the tetrahedral structure, right, that has been detected. Exact monomeric structure can be found in the ISM. So doesn't it highlight, how rich the chemistry is vis-a-vis the chemistry that is found on Earth, right? And all these molecules that have been detected in space, they help us understand what a significant trove of new chemistry is waiting to be discovered. For example, this H3O plus molecule can react with any molecule that has a basic entity. For example, with ammonia also, with formaldehyde, with this HCCN molecule, any molecule that has a basic entity, it can just donate a proton. And look at the scope it provides for enhancing the evolution of molecules in space. All right. So in this lecture, we discussed starting with some diatomics. We moved on to some tetraatomics, and I stopped with the example of H3O plus. In the next lecture, I shall be discussing a very interesting tetraatomic. I shall start again with tetraatomics and move further. But the next tetraatomic molecule we shall be discussing is going to be very interesting. So stay tuned for the next lecture. Thanks a lot. Have a good day.